In this video, we look at a Gaussian random process. We look at the random process xt. Let's look at the time slot t1, t2, and up to t of n. And this small n is any integers. N can be equals to 1, n equals to 2, n equals to 3, n equals to 10, whatever. So any n. Then we look at the random variables at that time slot. So x t1, x t2, x t3, and up to x t of 10, and go on. For random process xt to be Gaussian, any time slot xt1 has to be a Gaussian random variable, and any two random variables here, it has to be jointly Gaussian, and x t1, x t2, and x t3. And then if we look at these three random variables together, and this 3 has to be jointly Gaussian, and up to, if we look at all of this, that will be x t1, x t2, all of those random variables up to x t of n. And remember, n is arbitrary integer. And then we look at all of these random variables, and they are jointly Gaussian. If random process ext has these properties, then this random process is a Gaussian random process. Next, let's look at the white process. A random process xt is a white process if its spectral density is a constant, which means that if I plot the spectral density is a constant from all frequency from minus infinity to infinity. And we know the power in the random process, in any random process, that's the integral of the power spectral density from all the frequency here from minus infinity to infinity. Then if EXF, the power spectral density is a constant, then the power is equals to infinity. There is no practical system literally will have infinite power. So strictly speaking, white process is not meaningful physical process. But why we want to define the white process? Because a lot of random process in practical systems can be approximated by a white process. And also white process has a very good property that make analysis of the system easier. So let's look at the thermal noise in communication systems. At the receiver, when we make the measurements are subject to the thermal noise. In other words, the measurements at the receiver are corrupted by the thermal noise. By the quantum mechanical analysis, the power spectral density has this format. So the power spectral density of thermal noise is equal to h bar. H bar is a constant, is called Planck's constant. And K is Boltzmann's constant is given. T is the temperature in Kelvin. If we plot this power spectral density, it's very flat in a large range of frequency. If AF equals 0, and this power spectral density reach the maximum, that's equals KT divided by 2. And if we plot it, we found this power spectral density is very flat. For example, at frequency at double of 10 to the power 12 hertz, this is a very high frequency. The power spectral density dropped to 90% of the maximum value, which means only drop 10%, which is minimum considering this wide range of frequency. So therefore, in practical system, thermal noise is modeled as a white process. what is the power spectral density? That is a kT divided by 2. And normally kT is shorthanded by N naught. Therefore, the power spectral density for the thermal noise is approximately is N naught divided by 2. So if we plot it, so this is the frequency, this is the power spectral density of thermal noise. It is a constant power spectral density with the magnitude N naught divided by 2. And because this power spectral density is spread out from minus infinity to infinity, it is also called two-sided power spectral density. If the power spectral density is a constant in frequency domain, then what is the autocorrelation of this random process? The autocorrelation are N tau. En means noise, and here En is noise, is a random process. It's the inverse Fourier transform of power spectral density, right? That equals N naught divided by 2, that's theta tau. What does this mean? This means this random process, Rn tau equals to expectation of n t plus tau and n of t. And this equals to N naught divided by 2 theta tau, which means that equals to N naught divided by 2 when tau equals to 0, and tau if not equals to 0, that equals 0, which means that this random process, if tau not equals 0, n plus tau and t, they are two different time slots. So if we look at these two random variables, if we take product and we take expectation, then it is equal to 0. In this case, these two random variables are uncorrelated. So wide process, if we look at any two different time instant, the random variables at those two time instants are uncorrelated. R tau is non-zero only when tau equals 0. Because when tau equals 0, you look at the expectation of the two random variables at the same time instant. So therefore, of course, they are correlated. They are always correlated by themselves. Therefore, this is not equals to 0. In communication system, we want to know thermal noise can be modeled as a zero mean, wide, Gaussian, random process. The power spectral density is N naught divided by 2. So this is a model for the noise in communication systems.